The way you calculate the determinant of a 2 by 2 matrix is by using the formula AD minus BC. So here we have an example. If you wanted to find the determinant of this matrix, we would multiply 2 by 5, which is 10, and subtract that by 3 times 4, or 12, resulting in negative 2. Now, another property of the determinant is that it can be used to, well, determine whether a matrix has an inverse. If the determinant is 0, it has no inverse. In our case, however, we do have an inverse. So if we wanted to solve this equation for matrix A, B, C, D, we can multiply both sides by the inverse of the first matrix. Now, this results in the identity matrix. Multiplying any matrix by the identity matrix results in itself. It's kind of like if you multiplied a term by 1. So we can now isolate A, B, C, D. But how do we actually get the inverse of 2, 4, 3, 5? Well, you could do row reduction, but there's a neat formula for the inverse of a 2 by 2 matrix. It's just 1 over AD minus BC times matrix D, negative B, negative C, A. Notice how the denominator of this fraction is the determinant. So plugging this formula in, we get negative 1/2 times matrix 5, negative 4, negative 3, and 2. And after that, it's just scalar multiplication. Multiply each term by negative 1/2, and we get this result. Now, and after that, basic matrix multiplication gives us our final answer. Multiply the top row by each column, and do the same thing for the bottom row. And you get 3, 1, 0, 2. Another fun application of determinants is that you can use them to find the area of polygons. Here's a triangle with points negative 1, 3, 2, 9, and 5, negative 6. The area of this triangle is equal to 1/2 times the determinant of the 3 by 3 matrix composed of the points. And we fill the last column with 1s to make it a square. But how do we actually get the determinant of a 3 by 3 matrix? Well, the standard way to do it would be to pick any one of the rows. It can be top, middle, or last. Or, on the other hand, you could pick any one of the columns, first, second, or third. In this case, I'll pick the first column. Now we'll go through each element in this column and its corresponding row. Form a square matrix of the elements that are not in the column or the row, and multiply its determinant by the element. And I want you to also notice that's negative 1. You need to multiply the product by a negative 1 to a certain power resulting from the row index and the column index of the intersection. In this case, negative 1 has row index 1 and column index 1, so the power would be 2. It's really important to remember that indices start with 1 and not 0. Now, you can do the same thing for the other two elements. And we can use the formula from earlier to calculate each of these 2 by 2 determinants. And if you do the arithmetic, the expression evaluates to negative 63. So back to our area problem, the area is 1/2 of negative 63, or negative 31.5. And, just take the absolute value because area can't be negative. As we get bigger, the basic algorithm still applies. Pick a row or column, go through each element, and multiply by the determinant of the square matrix formed by the elements not in the selected row or column. Give them the right signs and add them all up. After 3 by 3, this process becomes incredibly tedious, but your choice of row or column can make the job significantly easier for you. Now, alternatively, you could use the Leibniz formula, which my good friend Nathan Burkett explains very clearly in this video, and I think it's also where the shoelace theorem comes from. But I want to focus on how easy some problems can be with this algorithm. Let's take this matrix, for example. I'm going to pick the bottom row because all but one of its elements are 0. This means that I only have to pay attention to the last element. Our solution is going to be A times the determinant of this 4 by 4 matrix. Of that 4 by 4 matrix, we also pick the row with the most zeros. So our solution becomes A times the determinant of this 3 by 3. Now we do the same thing and pick the last row of the 3 by 3 and multiply it by the determinant of the 2 by 2. From our formula, we know that it's going to be A times D minus B times C. So in our case, it's A times A minus 0 times A. And if you evaluate this whole expression, it gives you A to the 5th. So yeah, that's the standard way of getting a determinant. Sorry about the quality of this video. I have COVID actually right now, but I needed to get the voiceovers in before Monday. So thanks guys. Thanks for watching. See ya.